This is part 14 of the series Applications of Differentiation, and we're going to do another curve sketching example here. This example is going to be a little bit different than the previous ones, and we have a radical expression in this case. So first, once again, let's jump in and do our intercepts. So our x-intercepts, we can see that the denominator or the numerator is going to be 0 at x equals 0. So we don't really have to do a lot of work there. Our x-intercept is going to be 0. Okay. The y-intercept is going to occur at 0 over the square root of 0 squared plus 2, which is 0 over 2, which is just 0. So our y-intercept is 0 as well. So both our x and y intercepts are at 0, 0. Now, let's take a look at the asymptotes of this function. So this denominator never goes to 0. So this function isn't undefined anywhere. So for vertical asymptotes, it has none. Now, what about horizontal asymptotes? Well, because this is a radical function, it's likely that this function is going to have two asymptotes, one to the left and one to the right. So we're going to have to work this out to try and find out what those asymptotes are. So let's get started with that. So the limit as x approaches infinity of x over square root of x squared plus 2. In order to get this one isolated so that we don't have this conflict with the indeterminate form, we're going to divide both the numerator and denominator by x. So we have x over, now to get the x inside here, we're going to divide this by the square root of x squared. So that gives us the square root of x squared plus 2 over the square root of x squared, which gives us 1 over the square root of x squared over x squared plus 2 over x squared. We've gone over this technique before in previous operations. So this will be 1 over the square root of 1 plus 2 over x squared. When we take this limit, as x goes to infinity, this goes to 0, and our limit is going to be 1. And now because we may have two asymptotes, we're going to have to do this same thing, only we're going to have to take the limit as x approaches negative infinity. So let's do that. And in this case, we're going to divide the numerator and denominator again by x, but because we're going in the negative direction, the x value is going to be negative already. So let's give ourselves a little room. And so we divide the numerator by x. And when we divide the denominator by the square root of x squared, we're actually going to have to do something a little peculiar. X squared plus 2 divided by negative square root of x squared. The reason for this, of course, is because if this value is already negative, because we're on the negative side of 0, squaring it makes this negative x positive. We have to force it negative with this negative sign out here. So this gives us 1 over negative square root of x squared over x squared plus 2 over x squared. And that results in the limit as x approaches negative infinity of 1 over the negative square root of 1 plus 2 over x squared. When we take that limit, this goes to 0, and we're left with negative 1. So that gives us two horizontal asymptotes. One at y equals 1 and one at y equals -1. Okay, so there's our vertical and our horizontal asymptotes. And because it has a horizontal asymptote, it's not going to have a slant asymptote. Now what we're going to want to do is our first derivative to locate our extrema. So let's come back up here and grab our function, and let's start taking our first derivative. So f prime of x is low, which is x squared plus 2 to the 1/2 power. D high, derivative of the high term is just 1, minus high times the derivative of the low, which is 1/2 x squared plus 2 to the -1/2 times the derivative of the inside piece, which is 2x. So that's low, d high minus high, d low, all over low squared. And the square root of something squared is just that thing. So let's go ahead and simplify this beast. We have x squared plus 2 to the 1/2 minus, now in the numerator, this guy and this guy are going to go away. We're going to have x times x. So we're going to have x squared over this thing. Goes to the denominator because of that negative exponent. X squared plus 2 to the 1/2. And this whole thing is over x squared plus 2. All right, now we've got to multiply these out. So we have this times this gives us x squared plus 2 minus x squared all over x squared plus 2 to the 1/2. And the entire thing is over x squared plus 2, which is this denominator. Now, I want to simplify this thing, so looking at this, we know that this is just x squared plus 2 over 1. I'm going to get rid of this division by taking the reciprocal of this denominator and multiplying it by that guy. So what we're going to end up having then is this x squared and this x squared cancel out. So I have 2 over x squared plus 2 to the 1/2. That's this piece, times 1 over x squared plus 2. That's this piece. And when I combine these terms, I have 2 over this times this gives me x squared plus 2 to the 3/2 power, because this is 2 over 2, 1 over 2, add them together. 2 over 2 plus 1 over 2 is 3 over 2. This then is our first derivative, f prime of x. Now after all that, we look into this and we see that the numerator is never going to be 0, so it has no x-intercepts, and the denominator can't be 0 because of this squared term, so the function is never undefined. So this function has, this derivative has no critical numbers, so the original function has no max and min values, no extrema. So now, what we're going to have to do is go on to our second derivative and determine concavity. So before I do that, I'm going to make a quick modification here, just so that it makes it easier for us to work with this. just so that I don't have to use the quotient rule. So f double prime of x equals, pull the 2 out, and it's negative 3 halves times the inner function, subtract 1, which gives us negative 5 halves times the derivative of the inside, 2x. Simplifying this 2 and this 2 cancel out, and we have 2 times negative 3 times x, which is negative 6x over this denominator, x squared plus 2 to the 5 halves power. Now we can see that this numerator has a 0 at x equals 0. So we have a potential point of inflection at x equals 0. And the denominator, again, is never going to be 0. So this is our only potential point of inflection. So let's go ahead and determine concavity and whether or not that's a point of inflection. So 0, negative 1, and 1. And now let's evaluate our second derivative at those test intervals. So at negative 1, our second derivative is positive. So we're concave up from negative infinity to 0. And it's negative at 1. So we're concave down from 0 to infinity. And so now let's see if we can put all this together into the graph of a function. So here's our grid. We have a y-intercept at 0, 0 and an x-intercept at 0, 0. So we know that right here is our x and y-intercept. We don't have any extrema. We have no vertical asymptotes, but we have a horizontal asymptote at y equals 1. There's that. And a horizontal asymptote at y equals negative 1. That. And the critical piece in this particular function is the fact that from negative infinity to 0, we're concave up, which means the function is going to have to be doing something like this, as opposed to something like that. So we know that the function's going along this way, and we know that it's concave down on this other interval, meaning this is a point of inflection. So it's going to be doing something like that. And so that's a rough sketch of the graph of our function, just using analytical techniques. I hope this was useful to you. Now let's move on to the next section.